Hello YouTube. I'm trying to do this in one take. Let's hope it works. Video entitled Flat Earth, the Impossible Horizon. Is the horizon we see on the real flat Earth actually possible on a flat Earth? And this is part one of two parts. The second part deals with something somewhat different to do with the horizon. So if we can click on, yeah. So first I'd like to ask a question, is it possible to have two horizons on a flat Earth? Now what do I mean by two horizons? Well, if you look out across water towards some land, then you effectively have two horizons. You have a water horizon, or you can have a water horizon, where the water meets the land. And if there is a horizon there, rather than seeing right through to the shore level of the land, then it's a true horizon. And then you'll have a horizon between the land and the sky. And that's what I mean by two horizons. Now, of course, you can have two horizons. You could have two horizons where it's land meeting land and then land meeting sky. So if you had a range of hills and then another range of hills that were taller in the distance, then you would effectively have two horizons. And of course, if the range of hills in the distance is not taller than the ones closer to you, you only have one horizon. You can't see through a hill to the distance. And you can have multiple horizons in this way. And the same applies on a spherical or spheroid or geoid shaped Earth. Just to stop people criticizing, yes, if the further away hill, or mountain range, even though it's taller than the ones in front, if it's far enough away, it'll go round the curve of the Earth and it will not be visible. But if it's close enough, then it will still be visible. And this is the sort of thing that we see in reality. Okay, here you've got multiple horizons created by hills in the foreground and taller hills and mountains in the background. And you can get two horizons another way. That is, if you have a valley or a canyon of some sort. And the same thing again applies on a spheroid Earth. For example, the Grand Canyon. This wall is providing a horizon for us. This is part of the near side bank of the canyon, and this part is providing a horizon. I guess this is even a sort of vertical horizon. And you have another horizon here called on the far side, and then the true horizon between the sky and the land in the background. So multiple horizons are perfectly possible on a flat Earth and perfectly possible on a spherical Earth. Now let's talk about water, because we're going to look at horizons over water. And flat earthers like to repeat the phrase, water always finds its own level. This is true, but level only means level on a flat Earth. So on a flat Earth, level means flat. But on a spherical Earth, level means that it's actually equidistant from the center of the sphere or the center of gravity. So this diagram at the bottom shows curved water, which is actually level. Not flat, but level. It's the same distance from the center of gravity or the center of the sphere. Now, my question is, and this is the important question for flat earthers, how is it possible for water to create a horizon if the Earth is flat? We do a diagram placing a person on flat Earth with flat water. Looking at land across that water, the only horizon will be the horizon that the land makes with the sky. There cannot be another horizon. This person has a clear view of all the land on the opposite side, clear view of the surface of the water all the way to that land. And there's no reason, no obstruction at all that should prevent that from happening, from them seeing everything that is within their field of view. So there's going to be no horizon here, and likewise no horizon anywhere across the water at all. It will simply be a point at which the water meets the land. And this is not a horizon because it doesn't block anything. No horizon. So now consider the same example on a spheroid Earth. This is not unknown or untalked about. Most people understand this is what happens. So again, we have our sky to land horizon. But on this occasion, the view from our observer to the land on the opposite side is blocked by the curvature. They'll see this water here and all the water on this side, but they can't see any water beyond this point. And it'll also block out some of the land on this side as well. So we have a second horizon at some point near to where the line of sight starts to strike the water. So that's the theory. What do we actually observe in real life? Well, this, I would suggest, is a true water horizon. How do we know that? Well, this ship appears to be on the horizon or very close to the horizon. You can see the bulge at the bottom of the hull here. Don't be fooled by that line appearing to be something. It isn't. The water line is along here. This is something, the coincidence, there's something on the land in the background that stops at the same level here as the colour of the hull changes somewhat. And then there's reflection of light and so on the hull here, which is again changing colour slightly. But there's a hard water horizon. The ship seems to be on that horizon. This ship over here, we can only see part of the ship. Most of the hull is missing. It's a very similar ship, not the same. If you look at the above deck area, it's quite different. But it's similar, and it appears to be cut off just below the top of the hull there. So the horizon, which is water, is obscuring our view of this ship. Now, if we look at another example on the same day, taken from a lower elevation, we see even more clearly the water horizon. So this ship is now, the horizon has actually moved closer to us because we've lowered our elevation height, and the ship, as we might expect, has become obscured by that closer horizon. The same with the land here. That is also obscured by the horizon. And the other ship is now almost completely invisible with just the top of its bridge area here, probably the radar tower or a chimney from the engine or something, and maybe the top of the crane derry thing there. But clearly a lot of land is missing, the ships are missing. So we have a genuine water horizon. Can you see two horizons, flat earthers? Or are you going to deny that this is a water horizon? First horizon here, land to sky. Second horizon is here. First horizon, land to sky. Second horizon here, water to land. So if you're going to claim that that's a water horizon, rather than just put your fingers in your ears, cover your eyes and sing la 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 and pretend it didn't happen, you're going to actually accept what is obvious, that there is a water horizon in those images, then either you're going to have to claim that this is what is reality on a flat Earth, that is, that water bulges for some unspecified reason, and you're going to need to specify a reason if you're going to make such a claim, and effectively you're simply adopting the spherical Earth model and trying to stick it onto your flat Earth, which is an absurd thing to do. Or perhaps you think this is the explanation, that there is a valley between the observer and the ship, and that's creating the horizon at this point here. And that would kind of explain if the observer height was lower, then you'd see less of the ship. But how do you get a valley like this in water if water finds its own level? So if you're going to adopt either of these explanations, water doesn't find its own level, and yet we know it does. So is there an alternative explanation? Well, there is the dirty air hypothesis. Now, this has received relatively little attention. Most people just scoff at it and laugh at it. It's never been properly explained, not to my knowledge anyway. And it seems to go something like this. You have an observer looking out across flat water at land on the opposite bank, and there's land sky horizon. And although you'd think they could see directly through to the land on the opposite side, there is dirty air in between them and the objects that are going to be obscured. And the story goes that the more of the dirty air you look through, the more it's obscured behind it. And the dirty air is some unspecified low height near to the water. Above this height, everything seems to be fine and you can see as far as you need to see. But below this height, you start to look through dirty air and can't see so much. Now, they might argue this dirty air extends all the way back and looking through it at an angle. The question is, what would such a phenomenon actually look like in real life? Where would the horizon be for a start? How much dirty air causes a horizon to occur? But more important is, what should it look like in reality if that was the case? This is what we see in reality. One horizon, a second horizon. Do we see this? Do we see a layer of impenetrable air that we cannot see through, that obscures our view of things, with water below and land above? I would argue that we don't. Where is the layer of dirty air in this picture? There is no layer of dirty air in this picture. The ship here is not hidden by dirty air, it's hidden by water. You can see it. So let's not mess around with a dirty air hypothesis unless you can actually produce some evidence that it occurs. Not just that you see strange optical effects on certain occasions over water, but that this sort of thing is responsible for the water horizon. and the horizon is between water and the dirty air, not between the water and the land, or water and the objects that are on the ocean beyond the horizon. So just to say again, this is what we see in reality. We see a hard water to land horizon. This matches the spherical Earth model and not any flat Earth model at all. Now, what is more, the horizon changes position when the observer changes elevation. This is shown in these two pictures. And that's going to be where we start part 2 of this discussion about the horizon. Because not only should the horizon on a flat Earth, not only is it impossible in a situation where you're looking at land, it's also impossible when you're just looking out over the ocean and all you have is a sky to see horizon. But we'll look at that in part 2. So thanks for watching, and if any flat earther can explain how water forms a horizon on a flat Earth, please let me know in the comments, or come onto my channel and present your evidence. I'm trying to hold twice weekly opportunities for flat earthers to have at least 15 minutes of uninterrupted time to present some evidence of a flat Earth, and how a water horizon forms on a flat Earth would be very appropriate, very welcome. You have the opportunity after that presentation to engage in a short question and answer session with me if you wish to, and if you don't wish to, you can just present your evidence and leave. It's up to you. So it's a pretty good opportunity, so why not take advantage of it? And finally, I must give credit to Al K, fellow YouTuber, who produced or took these photographs and allowed me to use them. He actually gave permission several months ago, so I hope he hasn't changed his mind. They're great photographs illustrating very clearly the effect of the water horizon and elevation. So thanks, Al. Thanks for watching, and hopefully I'll hear from some flat earthers who want to explain how a horizon forms.